Hello, this is section 5.7, interpreting graphs of linear functions. Okay, so in our first example here, we're going to take a look at some information regarding dog sled travel. So team 1 versus team 2. So we've got two different tables here. Team 1, after 0 hours, is starting 100 kilometers away from a cabin. After 1 hour, we're going to say that they're 80 kilometers away. So I'm going to give you the rest of these the rest of the information to fill out here. After 2 hours, they're 60 kilometers away. After 3 hours, they're 40 kilometers away. After 4 hours, they're 20 kilometers away. And after 5 hours, they're 0 kilometers away, which means they must have been traveling back toward the cabin. Team 2, at 0 hours, was 0 distance from the cabin. Okay, after 1 hour, they were 25 kilometers away from the cabin. After 2 hours, they were 50 kilometers away from the cabin. We're going to continue this pattern. So of 3 hours, 75 kilometers, and 4 hours, 100 kilometers. So one of the teams was traveling toward the cabin. Team 2 was traveling away from the cabin. So we want to figure out the average speed for each of these teams. Well, this team appeared to be going 20 kilometers per hour. Okay, this team appeared to be going a little faster. It only took them 4 hours to go 100 kilometers. And so they were going 25 kilometers per hour. So that extra little bit of speed, that extra 5 kilometers per hour, got them there in 4 hours instead of 5 hours. So what would the graphs of each of these look like? Where would it cross the vertical axis, that's the up and down or y-axis? Where would it cross the horizontal or x-axis? What's the rate of change and what units does this have? Okay, so we're going to go ahead and actually plot some of this information on these graphs. So team 1, actually I should scroll up here so we can see it all. Team 1 was 0, 0. So along the bottom here, I need to have my hours. And so it works out nicely just to go 1 square, pardon me, that's 4, 1 square per hour. Here we need to go all the way up to 100, and it seems like I can go up 20, 40, 60, 80, and 100. And this is a very simple graph. After 0 hours, they started at 100 kilometers away. After 1 hour, they're at 80. 2 is at 60, 3 at 40, 4 at 20, and they were back home at a distance of 0. We're back at the cabin after 5 hours. We need to label these two graphs. I think it's fine to call these two graphs the graphs of team 1 and team 2. Don't forget we need a label here. So this one is going to be distance in kilometers. And I'm going to rotate that there as best as I can. Okay, and along the bottom, this is going to be time in hours. Okay, on this one, again, it's going to be time in hours. And along the side here, it's also going to be distance in kilometers. Okay, so now we'll do our scales, which is kind of like our ruler tick marks. And we're going to go 1, 2, 3, 4, 5 again. And here we need to go all the way up to 100. I'm going to use the same scale as I did before. You could go up by 25s, but I like to be able to compare my two graphs. And so I'm going to choose to actually do it this way, even though it's a little bit more awkward. I have to estimate a little bit. So after 1 hour, they'd gone 25. Well, that would be 30. So 25 would be about there. After 2 hours, they'd gone 50, which is halfway between 40 and 60. After 3 hours, 75. After 4 hours, 100. And I am going to draw the lines on these just to show the different slopes of these lines. So here's our first one, and that these are in fact linear. And these people did start at 0, 0. I forgot to plot that point, but there was 0, 0. I should probably go back and write that. It just wasn't on our screen. Oops. Okay, so as you can see, this is a steeper line than that one, meaning this team was traveling faster. Okay, so let's go ahead and fill out some of these blanks here. So the blank of a graph is the point where the graph intersects the horizontal. We're going to call that one the x-intercept. And it is also called the horizontal intercept. So what that means on the first graph here, the x-intercept was where we hit the horizontal axis. Here, that was our horizontal intercept on the second graph. Now, on to the next set of blanks. The y-intercept of the graph is the point where it intersects the vertical axis, also called the vertical intercept. I guess some people call it that, but honestly, it's almost always called the y-intercept. So we're going to go ahead and show what the y-intercept of each graph is. So the y-intercept would be the same, actually, on this one. This is the y-axis, and it hits it at 0. So that's an interesting thing about this graph. The y-intercept and the x-intercept happen to be the same. Here, they're different. Okay, so a little bit about describing a linear function. So I'm actually going to cross out the word is, because I'm going to use a bit of another description here. So I'm going to give 3 points about what makes something a linear function. So linear function is any graph of a line that is not vertical. Now, why can't it be vertical? Pardon my typing here. Because remember, it has to pass the vertical line test, and a vertical line itself would not do that. So any other line other than a straight up and down line is called a linear function. Okay, it has a constant rate of change. That means the staircase doesn't change as the line goes on, just like we were talking about in the last section. And it has a variable to the power 1, which doesn't mean a lot to you right now, but as you go on to future math classes, you will examine functions that have powers of 2 and 3. And so we just want to make a note of that here, that this is the power of 1, meaning there's no exponents on our variables other than 1. Okay, so let's go on and take a look at the next page here. So example 1, determining intercepts, domain, and range of the graph of a linear function. So what are the coordinates of the horizontal intercept? So the horizontal intercept is, think of the horizon, it's flat. So where does our graph hit this axis? And it hits here, which is 45. Now we should put units on that as well. And it looks like the units along the bottom are time in minutes. So that's going to be 45 minutes. Oh, sorry, it asked for the coordinates. My goodness. Okay, so then we want to say that as an ordered pair. So that would have been 45 minutes, comma, 0 centimeters. This one's height on the left, height of a burning candle. What are the coordinates of the vertical intercept? So this one is a time of 0 minutes, but a height of 2, 4, 6, 8, 10 centimeters. What does the horizontal intercept represent? Well, when the height of the candle is down to 0, that means there's no candle left. So it represents the time at which the candle is completely burnt out, which is 45 minutes. And the vertical intercept represents the height of the candle before it was lit. Now, if we're going to write out the domain and range, mathematically speaking, the domain would be any values between 0 and 45, but it couldn't go past 45 because the candle would have disappeared. It would have been all gone after 45 minutes. But it could have been anything in between there. It could have been 5 minutes. It could have been at 11 minutes. It could have been at 10 and a half minutes. So all of the values in between are important. And so how we write that is we put our lowest value on the left, we put our time in the middle, and we put our highest possible value on the right. And then we put our less than or equal to signs, and we put our curly brackets on each side, saying it's the set of all the numbers, all the time values between 0 and 45. I cannot list them out and put commas between them because it's infinite. There's an infinite number of time values, so this is the only proper way I can write it. And we are allowed to have 0 as a value, and we're allowed to have 45 as a value, hence why they can be less than or equal to. For our range, we're going to do the same thing, except this time the range has to do with height. And so our lowest possible height is 0, and our highest possible height of the candle was 10. Are there any restrictions on the domain and range? Well, yes, there are. For example, the candle can't have a negative height. And also, it can't burn once it's all gone. So it can't continue to burn after the height is 0. What's the rate of change for the candle height? So remember our formula from our last lesson. The rate is going to be the change in dependent over the change in independent. So this time the dependent was the height. So it changed from 10 centimeters over a period of 45 minutes. So 10 centimeters over 45 minutes, if you divide that up in your calculator, you get 0.2 repeating. So I'm just going to put the bar on top to represent that. And that is centimeters per minute. So how quickly was the candle melting? It was melting 0.222222 centimeters each minute. Seems reasonable for a candle. Okay, going ahead now and looking at example 2, sketching a graph of a linear function in function notation. So remember function notation from earlier in the semester, we say f of x. It's a fancy way of also just thinking of an equation of y equals 4x minus 3. It's really the same thing. It's just a special way of writing it. That's the notation. So when x equals 0, we would have our y-intercept. Well, why is that the case? So this is our y-axis. This is our x-axis. If we want to find our y-intercept, it could be anywhere on this line, but no matter where you are on this line, your x value is always 0. Okay, so we're going to set x equal to 0 and find our y value. So I'm going to say, hey, what's the value of my function when x equals 0? Well, that would be 4 times 0 minus 3, which is 0 minus 3, which is negative 3. So the y-intercept is negative 3. So that means on my y-axis, I'm going to go down to negative 3, and there's my y-intercept. I'm just going to switch colors here and find the x-intercept. So that would be when my y value is equal to 0. Now I'm going to solve for x. I'm going to add 3 to each side. So I get 3 equals 4x. I'm going to divide each side by 4. So 3/4 is my x value, or my x-intercept. Now, that's okay. We can have a fractional x-intercept. I just have to think about where to put that. So there's 0, there's 1. So 3/4 would be approximately there. Now, is that enough information to draw a line? Yes, it is. The great thing about lines is you technically only need 2 points. And as soon as you connect those 2 points, you have drawn your line. So here is the line represented by that function because I was able to find 2 points. As soon as I find those 2 points, I can go ahead and connect them and draw my line. And I'm going to put arrows on them so it's a little bit messy, just to show that that line can go on forever in either direction. Okay, the last 2 examples here. So example 3, matching a graph to a given rate of change and vertical intercept. I'm going to zoom in a little bit here. Oh, actually, we're fairly zoomed in. I'll leave it there. So which graph has a rate of change of -5 and a vertical intercept of 100? Justify your answer. So let's take a look at these 2 graphs to see what we can come up with here. So they both appear to have a vertical intercept of 100. So they both have that because look at this. There's 100. There's 100. So they both have that. I guess the question is which one has a rate of change of -5? Well, if it's a -5, that means it must be going downward. And so this one works, but this one does not. So it's going to be A. And I think we've shown enough work there to justify our answer. Example 4, solving a problem involving a linear function. The graph below shows the total cost for a house call by an electrician for up to 6 hours of work. Okay, so it looks like there's an initial cost, and then as the electrician continues to work, the cost goes up. So if you receive a bill for $210 after the electrician completes the job, how many hours did she work? Okay, well, let's take a look. So we can actually do this a couple ways. First, let's just for fun estimate it, and then afterward we actually will calculate it out. So if we were to estimate and take a guess based on this graph, right now it looks like a bill of $210 would be somewhere in between 120 and 240. And this appears like it's going up by 60. So this would be 60, 120, 180. So 210 would be halfway. So 210 would be about here, if I'm going to guess. So if I go all the way over here and then try to go down, I would say that my estimate would be about 4 hours. Okay, so that's just by guessing, looking up the graph. But I don't feel super confident in that. It's a little bit messy. You know, we're still guessing at where things are landing. So it's purely a guess. What we are going to do here is figure out a few things to come up with a formula so that we can actually calculate this. So first, we're going to find the rate of change for this question. So the rate is the change in dependent over the change in independent. And here, it seems like it went up $120 over 3 hours. Now, how do I know that? I'm going to draw a helpful triangle between these two dots. So from this dot over and this dot up. So these two dots I feel confident about, these red dots, because they're provided and they land right on grid points. And so if I look at those two dots, I can see that this went up 2 squares, which is $120 over a period of 3 squares along here, which is 3 hours. So that allows me to do some calculations here, that it was $120 for 3 hours of work. Therefore, it appears to be $40, per hour. The second thing I need to find is the base fee, which is our y-intercept. And the base fee was here, which is $60. So below here, I'm going to show the calculation of how we can finish this question and find out the exact answer. The cost for this electrician is going to be $40 per hour times the number of hours plus the base fee. We know that the cost is $210. What we don't know is the number of hours. So I'm going to keep that as H. I'm going to go ahead and solve this question. So I'm going to subtract 60 from each side so I can start to isolate my H. And I end up with 150 is equal to 40 times H. Then I'm going to go ahead and divide each side by 40. So 150 divided by 40 ends up being 3.75 is H. Now, we've calculated the answer. We estimated that it was 4 hours by looking at the graph. It's actually 3.75 hours, so it's a good thing that we estimated, but we should always state our answer in a complete sentence. It's just to say H equals 3.75 doesn't necessarily mean anything. So we will say that the electrician would have worked for 3.75 hours. And there's a final statement clearly showing our correct answer and answering the question. Okay, that brings us to the end of this section. Thanks for watching the video. Feel free to watch it again or send me any feedback on the video. Thank you very much.